each of them separately. Okay? So the first component, by directly using UFD, you can prove that this polynomial is small. Tn power minus 4 just needs to replace all the values into UFD. Okay? This is exactly what we need to do. So we say that this value is smaller. This is the UCB index, smaller than R1's true value. And do some math. You get this form, plug it into UFD, and you get on the right bound this one. You get Tn power minus 4. No magic here. Element 3 now. Okay? You can do the same, exactly the same with the second term. You can also prove that the second term is also polynomially small. The only tricky part is the third term. But observe the following thing. So when the number of times we pull the wrong arm is high enough, meaning that it has to be at least 8 times the log t divided by square of delta, then actually it's not going to happen at all. Okay? Because if you do the math again, you're going to get that this term, if M2 is larger than this value, then actually this term will be smaller than delta. Just need to plug it in. Okay? Meaning that if M2 is large enough, and we go back here, M2 is large enough, then this one is not going to hold. Okay? And if this one is not going to hold, this one or this one has to be true. But if this one and this one has to be true, then we use this part. So the probability that at least one of them is true is going to be polynomially small. So putting all the things together, now we can say that the probability that the wrong arm has a higher index is going to be very small. Okay? If we make enough mistakes, after that it's going to be very small. So what does it mean that we didn't make enough mistakes? It means that if we pull this number of mistakes, we make this number of mistakes, after that we're not going to make a mistake anymore, or very unlikely to make a mistake. Okay? And this is the proof. Yeah, at the beginning you can make mistakes, and this is exactly what you see in us. You make mistake, but then after this number of mistakes, the chances that you will make a mistake again is very small. So it means that you will move to the best arm. You will start doing the best arm. Okay? So this is the proof for the two-arm case. For the multi-arm case, a little bit more complicated, but basically the same, almost the same. Okay? You can think about it later at home, or I can refer you to a paper for you to see the proof. But it's basic. So this is the essence of it. This is the core part of it. And so, okay. So just a summary before the break. So the reason I started with the stochastic matter of bandits is that it's a very simple model, seamless model, if you want to be bold, that can capture this exploration versus exploitation dilemma in decision making uncertainty. Any algorithms which are designed to matter and bandits are typically very simple. If you look at the UCB, the explanation behind it is complex. The proof that why it works are typically very complex. But to calculate the UCB index is simple. Computation is very efficient. So you can run online, you can run in big data sets, big databases. You can handle millions of users out there if you need to, because all the calculations are very simple. Okay? And in the afternoon, I plan to talk about the application domains as well, and they are very practical, especially if you are interested in AI, computer science, tech, so on and so forth. Okay? So let's have a break now. What's the time?
So.
Oh.
For the results so far, we just assume that it's stochastic and stationary distribution, right?
Yes, so this is a seamless case, yeah. So this is a...
So we didn't consider no stationary case, okay.
That's the next one.
And adversarial case.
Yeah, that's the next one.
Okay, good.
Okay.
Thank you.
So let's have a 5 minutes break because we are a little bit late.
Good. Before the break, any other questions?
Do we have a concrete example of the
Concrete example of the algorithm, like pseudocode,
Okay.
visualization or something?
For example, on a recommendation system, can you give the example where you use the multi-high bandits versus traditional algorithm like?
Okay. So think about collaborative filtering. Okay. So are you familiar with collaborative filtering? Okay. So you have items here. Okay. Item 1, item 2. Okay. You have user 1, user 2, user n. So basically, recommender matrix or preference matrix is a matrix where each value means that how likely this user will choose this item, right? And one thing you want to do is that you want to learn as possibly as accurate as possible the matrix, so then you have the full information about the behavior or the preferences of your population, right? And there are many versions of matrix completion, matrix factorization, or whatever. But those techniques are typically pure exploration, means that you need to do lots of random stuff. So the more scattered is samples, the better you can reconstruct the matrix. That's the statistical machine learning theory. But if you have the exploitation diagram, then it's different. It means that yes, suppose that you start with a almost empty or very sparse matrix. A lot of holes here, you don't know anything. Okay? So very difficult to do the matrix completion. But you need to be very quickly identify what is the most preferred item for this guy. Okay? So you say that if you just focus on collaborative filtering, then what you want to do is that you try a few things, scattered as possible. But if the guy, if you are unlucky and these things are very low scores, like 1, 1, or 1, then he will say that, okay, enough, I'm going to leave the system because it doesn't give me good value straight away. Okay? So the bandit, in this case, what we want to do is that we want to add on top of the collaborative filtering, we want to add a bandit, which means that now, while you are trying to learn the matrix itself, you also want to learn in the way that these values have to be high. These values that you show the item you show the user can be very high. And the trade-off here becomes challenging because what happens if all the high values are here in this column, right? Then it means that you keep